Hello everyone, let us start 19th lecture. And here we will talk about phase diagram and G versus X plot. So, this phase diagram we will talk, and then G versus X plot will be needed, which is the free energy composition, X is the mole fraction. That diagram would get me to draw a phase diagram. We will try to draw a simple phase diagram like isomorphous system, and or we can also draw eutectic system or eutectoid system. But let us get to the phase diagram, and when we talk about phase diagram we need to know what we do with the phase diagram. See, phase diagram tells me that in a system at a particular temperature or pressure, or let us say if it is a pure component, then at a particular temperature and pressure, what are the phases that are in equilibrium. Okay. And at the same time, if we consider a binary system, then the composition part would come into picture, and that time we need to consider the composition also as a variable, and that time we need to see at a particular temperature or at a particular pressure what would be the temperature and composition variable condition, and that time what would be the number of phases that will be in equilibrium. So, it talks about the stability of different phases. So, the phase diagram represents stability of different phases of a system, of course, of a system in equilibrium. In equilibrium as a function of different variables. Different variables. Now, whenever we try to, and this phase diagram, we can represent those stability of different phases in the form of a pictorial view, and that time it becomes a diagram depicting stability of phases. Now, in order to get to a little bit more about phase diagram, we need to understand few parameters. Of course, first thing it comes phase, as we have understood before, that chemically homogeneous, physically distinct part of a system. And we have already explained this phase in the earlier lectures, and that time this chemically homogeneous physically distinct part of a system will be surrounded by an interface which will separate this particular part from rest of the part of the system. Now, then we have to see the components. Component, they are chemical spaces, of course. Chemical spaces constituting the system, but these chemical spaces, they must be independent spaces. That means, for example, if we consider a phase like alpha phase in case of iron, which is ferrite. So, in the ferrite we have iron and carbon. So, that time ferrite is not that chemical species because it depends on iron and carbon. So, that means iron and carbon will be my two components. And then chemical species, that means they should be independent. Independent component. And then we have degrees of freedom. Which we consider as F, which tells me that in order to dictate a stability of different phases in equilibrium, we need to understand that what would be the number of variables that will be required to define that particular stability in that at that equilibrium. So, that now it tells me that it is not only the number of variables, rather it is the minimum number of variables that will be required, and that too they will be independent. So, minimum number of variables that will be required to define that particular stability of that particular phase. And here those variables are either temperature, pressure, composition. This C is basically the composition, or we can, C is basically the component. So, here we consider it in this form, this is P and this is F, and this C is basically the component, and the components we can mix together and form different compositions. For example, iron carbon system, this ferrite can exist in a different compositions. For example, it could have 0.001% weight percent carbon, 2.02, 0.025% carbon. So, in this whole range this ferrite can be possible. So, though that case we are changing the compositions, but the components would be remaining same, that means carbon and iron. So, now there is a relation which dictates how to calculate degrees of freedom while the phases are in equilibrium. Okay. So, now if we try to find out that relation is called phase rule, and the phase rule says that F equal to component minus P plus 2, and this 2 that is coming, this 2 number that comes from the contribution from pressure and temperature. So, those are external variables. Now, this will tell me that what would be the number of minimum independent variables required to define the system. Now, let us get into some of the phase diagrams. That means, let us see the pictorial view of the stability of different phases. And before we start the binary system, let us consider a simple single component system. And if we consider water, which is H2O, now in that case it is a single component system, and there I can have a phase diagram as a function of pressure and temperature, and the diagram looks like this. And here this is liquid, this is solid, and this is vapor. This is vapor. And now at this particular point, all the solid, liquid, vapor phases can coexist. So, this temp corresponds to 0.01 degree Celsius around, and then corresponding pressure is around 0.01 006 atmosphere. So, if I consider in the form of atmosphere, this is at that atmosphere pressure. And now we know that the melting temperature of water at 1 atmosphere pressure is 0 degree Celsius. So, if I consider a 1 atmosphere pressure, this is 1 atmosphere, and corresponding temperature we can get is this 0 degree Celsius. And similarly, we know that 100 degree Celsius is the boiling point of water at 1 atmosphere pressure. So, we just extend it, and then this one, this point is 100 degree Celsius. And of course, there is one more point which is called critical point. We are not getting into that. That appears at a much higher temperature and pressure, and the temperature is almost about 374 degrees Celsius, as well as the pressure is around 218 atmosphere. So, at that particular pressure, so if we consider very high pressure and high temperature, 374 degrees Celsius and 218 atmosphere pressure. So, this becomes a critical point where the water becomes supercritical. Okay. So, the water becomes supercritical. So, we are not looking at that particular situation, but we can see that within this boundary solid is stable, within this boundary is liquid is stable, and within this zone vapor is stable. And if we try to find out what would be the degrees of freedom at different points in this phase diagram, we can easily find out. Okay. So, for example, in this case, if I try to find out the degrees of freedom at this point would become C minus P plus 2, component is 1, phases, number of phases are 3, vapor, solid and liquid. So, 3 plus 2 equal to 0. Whenever we have the F value to be 0, which is the minimum value that is possible for F, that suggests that the maximum number of phases that can be in equilibrium. Okay. So, that time the maximum, there are 3 phases. So, the 3 phases can be equilibrium. Three phases are in equilibrium. Similarly, if I try to find out what would be the degrees of freedom on this line, so this F equal to again the same formula, but here the component is 1, that is water, but there are 2 phases. So, 1 minus 2 plus 2 equal to 1. What does it mean? It means that one of the variables, either pressure or temperature, that can be independently varied. Okay. For example, if I try to see, if I fix this pressure at this particular point, then automatically the temperature gets fixed. Similarly, if I change this pressure along this axis, I can see that the temperature is also correspondingly changing. Okay. So, that means that one of the variables can be independently varied. Similarly, if you see at any points on this line or on this line, you will see that the variable number of variables, independent variables would be 1. So, that means one variable can be changed independently. Okay. So, now if I try to see what would be the phase rule or the degrees of freedom at this point, there will be one phase, one component. So, that means the degrees of freedom at this point F would be 2, because C is 1, P is 1, P is 1, which is the vapor, and that means that F becomes 2. So, that means in order to define this particular point, we need to define pressure and temperature both. Okay. So, here situation was like this. If I define pressure, if I fix pressure, the temperature is automatically getting fixed. But here, in order to stay at this point, we need to fix both the pressure and temperature. Okay. For example, if I try to fix pressure, let us say let me fix the pressure. Okay. So, that means along this particular path I can get to any point. So, you can see that the temperature is also getting changed. Okay. So, that means that in order to define this particular point in a single phase for water one component system, I need to have 2 degrees of freedom. So, that means 2 independent variables will be required to define that particular point. So, that way we can find out what would be the degrees of freedom at different points on this particular diagram, but interesting is this one where the degrees of freedom becomes 0. Okay. And this point also is called invariant point. Invariant point. So, this is in case of simple single component system, and also we can see the pressure temperature regions where the solid would be stable, liquid would be stable and vapor would be stable. So, if I come back to the definition, the stability of different phases in equilibrium as a function of different variables, that particular definition is satisfied in this particular phase diagram. Now, let us get into little complicated phase diagram. Let us get into a kind of phase diagram, for example, a binary phase diagram. So, in order to do the binary phase diagram, whenever I am talking about binary, that means there would be 2 components. And this can have solid, it can be solid, liquid, both are possible. Now, we are not getting into the liquid situation, because our heat treatment things will be concentrating on the solid and solid liquid phase diagrams only. For example, in case of steel heat treatment, we will be only looking at the solid situation. But in case of let us say aluminum copper, there also will be looking at solid situation, but that particular phase diagram will be taking care of one particular type of phase diagrams which is called eutectic phase diagram. So, we will come to that. So, let us consider these 2 situations. Now, if I consider solid liquid situation, there will be number of possibilities. Okay. So, in case of solid liquid situation, for example, if A and B, these are 2 components. Okay. So, these 2 components can get mixed completely. So, what it means that soluble at any composition. Soluble at any composition. So, in this case either it can be 100% A or 100% B. 100% B. In between the composition range what we have, if I consider in terms of percentage of B, if we start from 100% A and then start adding B atom into A, then A will dissolve B completely from 0% B to 100% B. And whenever I am talking about 100% B, that means A is absent now. Okay. So, that means the completely soluble over the entire composition range. Now, this completely soluble at any composition, this can be applicable, this can be possible in liquid also or in solid also. See, if we consider that both liquid and solid, everywhere these 2 components will be soluble, completely soluble, then we come across one particular phase diagram which is called isomorphous. Isomorphous phase diagram. Now, in this case, will be fixing the pressure to be 1 atmosphere. Fine. If I fix the pressure at 1 atmosphere, then I would be left with again 2 more variables. One is temperature, which is the external variable, and the another one is composition, because over the entire range from 100% A to 100% B, there will be any composition that can be possible. So, now if once I fix pressure, then the phase diagram would be between temperature and composition. Now, in case of single component system, since there was no issue with the composition, because only one composition is possible, that means water. Okay. So, that time we had to draw this phase diagram as a function of pressure and temperature. But in this case, we are fixing one particular variable, which is pressure. So, that means 2 more variables will be left with, which are called temperature and composition, and the diagram will be between temperature and composition. So, now if I try to draw a temperature composition diagram, this is temperature, this is percentage of B, let us say. So, that means from 100% A to 100% B. If I try to draw the isomorphous phase diagram, that means both the components will be completely soluble in liquid as well as solid. The diagram looks like this. Okay. So, in this case, this becomes my liquid, this is solid plus liquid, and this is solid. Okay. And this particular line we call liquidus, and this line we call solidus. And this liquidus gives me the equilibrium situation between liquid and liquid plus solid, and this line indicates the equilibrium between solid plus liquid and solid. Now, this is 100% A, so we can term it as TMA. So, that means the melting point of A, and this one, since it is 100% B, we can term it as TMB, melting point of B, because at this point both the lines are merging together, and then if I try to see temperature time cooling curve, then cooling curve would look like, okay, it is a single component melting. Fine. So, and this point, as we have discussed, that this is coming due to recalescence. This is coming due to recalescence. Now, let us get to this particular diagram in a little, let us discuss this diagram a little more. Okay. So, let us come to this particular part. This is clear. Now, let us take one particular composition, let us say this composition. So, if I take this composition, let us say 60% B, and I melt this particular, let us say we start with 40% A atom and 60% B atom, and then I mix them together and I melt them and take it to this particular point, and at this point both the thing will dissolve together and form a single phase which is liquid. Now, once we form homogeneous liquid phase, means it becomes a single phase, that means it must be homogeneous. So, once we homogenize this particular thing and then create it, now let us start cooling it down, and once we cool it down, once it approaches this point, because this point is the boundary between liquid and liquid plus solid, at this point fast solid would appear. So, and as we keep going downward, we will increase the amount of solid, and finally once we reach to this point, a very little bit of liquid will be left, but rest all will be solid. And then once we reach to the single phase region, it will be again completely solid with a complete solubility of B in A. Now, if I try to find out the degrees of freedom at this point, F would be equal to, so there are how many phases? There will be 2 phases, which is, so that means if I try to see at this point what would be F, F would be equal to C minus P plus 2. Now, this plus 2 will be replaced with 1 because we have already fixed pressure. So, that means pressure is fixed. So, I am left with only one variable, external variable, which is temperature. So, now this would be C minus P plus 1, and here component, there will be 2 component, already we have decided this A and B. So, 2, and phases would be 2 because liquid and solid, plus 1 equal to 1. What does it mean? It means that in order to define this problem point, I need to have one independent variable, which if I fix that particular independent variable, so I will be left with, I can fix the second variable immediately, okay? Because if I fix this point, the other point, the composition is also getting fixed. Now, similarly, if I try to see what is the degrees of freedom here, again it will find that it would be 1. Now, if I try to see what would be the degrees of freedom at this place, this is C equal to C minus P plus 1 equal to F equal to C is 1, 2, P is 1, and this is 1, so 2. So, in order to define this point, I need to have 2 variables, the temperature as well as composition. But here I am fixing one variable, the one independent variable I can do with, I can define the variable, define the system. Now, if I try to see at this point, again you will find that the F would become 1. Now, you must be wondering that how can I make it F equal to 1, because this case I had F equal to 2, this case again you will find that F would be equal to 2, but at this point why it becomes 1. Now, in order to understand that, let us see a tie line construction. This tie line is nothing but a parallel line with the composition axis, and that actually gives me the idea of the fraction of different phases, and here we have 2 phases. So, along this tie line we can get the amount of liquid as well as solid, and that amount in the form of weight fraction, okay, because it comes from the mass balance. So, the amount of liquid and solid we can calculate, and once we come to this point, the liquid, if I try to take this liquid to this point and then hold it, immediately the liquid would be divided into two portions. One would be solid, the another would be liquid, and these liquid would have different composition, and these solid would have this composition, and these composition would be decided by the point on that particular line along that parallel line with respect to the composition axis. So, this is my tie line. Now, since I am seeing that once I am dropping this liquid to this point, the liquid is dissociated into liquid plus solid, and in this case this liquid has a different composition. Okay. So, that is why these particular phase, liquid phase, would have a different composition, and this particular phase, which is a solid, has this composition. Okay. And then we can fix the amount. So, we can see that at this point immediately we are reaching to these 2 points. We are not staying here because it dissociates. So, that is what at these points we have f equal to 1. So, it immediately tells me that f would be 1 at this point. Okay. So, we will continue our discussion on tie line as well as phase diagram, okay, in our next lecture. Thank you very much.